Number 55. Write resonance forms that describe the distribution of electrons in each of these molecules or ions. And then I see that I have A through E here. So let's just put A, we'll put B down here, and we'll work with C, and then we'll see where we can put D and E. Okay, so resonance forms comes from knowing how to draw Lewis structures. So without drawing the Lewis structures, we will never be able to find out the resonance structures, all right? So if you guys are not strong in your Lewis structures, go back to questions, I think 40 through 45 are really good examples in this textbook, and I've done those questions for you. So if you're on the playlist, just hit a few questions back, and I'll do them all with you guys there. So I'm going to assume that we know how to do the Lewis structures so that we can discuss resonance more in depth. All right, so for A, they're talking about, they want the resonance structures or the resonance forms for selenium dioxide, which is OSeO. Now, here, they're giving you the structure of what this compound actually looks like. It looks like there's an oxygen on the left, a selenium in the middle, and an oxygen on the right. So if we have done the Lewis structures properly, it would look something like this. So we have oxygen, that would be double bound to selenium, that would be another bond to oxygen, and then this would have two lone pairs, this oxygen would have two lone pairs, and this selenium would have one lone pair. Because selenium and oxygen both have 6 valence electrons, right? So the total here of this whole thing should be 18 electrons. So, and we have it here, 2, 4, 6, 8, 10, 12, 14, 16, 18. Now, just know that selenium can have an expanded octet, meaning that it can have more than 8 electrons if it's the central, and it can only have that if it's below period 2 on the periodic table. Boron all the way to neon is in period 2, so aluminum to argon would be period 3, and vice versa, well, et cetera, and selenium's all the way over here. So selenium can have an expanded octet if it's the central atom. Now let's talk about the resonance forms of this structure. Resonance forms basically just means that you can have different structures drawing-wise, but they have the same amount of total electrons. So all you're just doing is you're distributing electrons, but you're not violating any laws. You still want to keep that octet rule. The octet rule is saying that your electrons still want to share and have a total of 8 electrons. There are exceptions, but for majority of them, the outer electrons would want to have 8. Now, if we look here, this oxygen has 2, 4, 6, 8, and this oxygen has 2, 4, 6, 8. Now, let's try to draw another representation of this structure. Now, let's see. Once we start drawing resonance structures, we always put brackets. So that's a standard. So once I start drawing my resonance structures, I have to bracket all the structures off, and you will draw each resonance structure by giving an arrow. This represents that the structures, the total resonance structures combined, will flip-flop back and forth between as many structures as you write. Structures that have resonance forms are not stagnant. They constantly flip-flop back and forth between the structures that you draw. So let's analyze what a single bond is, right? One of these lines basically represents 2 electrons. So what I'm going to do is I'm going to, instead of have this bond here, I'm going to just get rid of it and pretend that there's 2 electrons here, right? Which technically would be one line of the bond. Now, you're going to just relocate the electrons. And look what happens. If I relocate these 2 electrons and I move them over to oxygen, is that violating the octet rule, or is that okay? Well, let's see. Oxygen will have 2, 4, 6, 8 electrons still. And now let's look at selenium. Selenium will lose these 2 electrons because these are purely with just this oxygen. But look what happens. 2, 4, 6, 8. So that has now the perfect octet rule. Doesn't have the expanded octet. So that could be another way of drawing this structure. So I'm just going to draw that over here. So we have now oxygen, selenium, and oxygen. But now instead of this being a double bond, it's going to be a single bond with a double bond on this side. We didn't touch this part, so this will stay exactly the same. There still was the 1 electron up here, but now this oxygen has the 3 pairs. And that's totally fine. So that means that this structure and this structure swap back and forth because they are resonance structures. And if you calculate all the total electrons, it still will be 18. You never add electrons, you never lose electrons, you always just distribute them to different elements or atoms. Okay. Well, now you just got to play fair, right? On this side, there's another oxygen here. So what could you have done with this electron? You could have technically done the same thing, right? Instead of drawing this one line, I could say that this was 2 electrons, and I'm just going to redistribute them, so these 2 will come over here. You see how that happens? So I have to draw another arrow, meaning that I have another resonance form. And now I will just put it on the bottom here. So oxygen. Now this one will have the double bond again, because now you're working off of this side. So now this would have the single bonded oxygen. And then this would have the 2 electrons. This would have the 1. And now this has the 3 pairs. We didn't add electrons. We didn't lose electrons. We just redistributed them to different atoms. So the same total electrons will still be 18, no matter which form you have, whether it's this one, or this one. But as you can see, it's 3 representations of the same compound. In the first one, you had 2 double bonds. In the second one, you had the single bond on the left and the double bond on the right. And then the vice versa for the third one. You had the double bond on the left and the single bond on the right. So you just got to cover all of your, cross your T's and dot your I's. Once you have done all of your resonance forms, you will bracket off saying that those are the only ones. And for this one, those are the only resonance structures. A is done. B, nitrate ion, which is NO3-. So we have to go back to learning how to do Lewis structures. You should come up with the compound that looks like this. I will put the double bonded O up top here. And you know what? I will do the lone pairs separately. So you should have this kind of backbone. Now I will just draw the lone pairs. This one should have 2. This one should have 3. And this one should have 3 as well. So hopefully you doing the Lewis structures, you get this form. But once again, if you're not strong, go back to those couple of questions. I promise you will get better if you watch those. Now we're just going to continue on. Now, in my drawing, I have the double bonded O up here. Well, could I have put the double bond over here? Yeah. And could I have put the double bond over here? Yeah. So you got to play fair. So this resonance form, I had the double bond up top. I will draw another resonance form where the double bond's on the left, and I will draw the other resonance form where the double bond is on the right. Now, I just want to show you how this actually happens. I'm going to pretend that this is really 2 electrons, right? So I'm just going to erase this line and put 2 dots here. So now in order for this to still satisfy the octet rule, it still has to have 8 electrons. So if I try to move these electrons over here, this oxygen will have 2, 4, 6 electrons. That's not good. So actually these 2 electrons will go back to this oxygen just by itself. Okay, so that takes care of that, right? So that one is going to have just the 2 dots. But now it looks like nitrogen needs a little help. 2, 4, 6 electrons. It wants the octet. So that's when one pair from the other atom will put its lone pairs back into the bond. So these 2 electrons will go into the bond, and that's how you will get your double bond here. That's how you redistribute your electrons. So I'm just going to erase this, keep that there, and now let's just draw our New resonance forms. We have nitrogen. Now there's going to be a single bonded oxygen, a double bonded oxygen here, and a single bonded oxygen here. Keeping the octet rule, this one now has only 2 lone pairs. This one has the 3 because of what we just discussed before, and this one has the 3 as well. Cool. Now you just got to play fair. We put the double bond over here, so the same type of reasoning would go to the double bond on the right-hand side. So I'm just going to redraw that. And I have to draw another line, and then we say N. This one will keep the single bond. This one will now have the single bond, and we'll throw the double bond over here. And now we just have to satisfy the octet rule. So this one will still have 3 pairs. This one will now only have 2. And this oxygen will have 3 pairs. And there you go. We played fair, right? We brought the double bond to all 3 of these oxygens, and that's the end of the road for this one. So now I will box this off, meaning that the resonance forms are done, but now I see that I had a charge. You have to keep the charge in the upper right-hand corner. So if they give you a charge, you have to keep it there, just to show them that you did gain 1 electron. Okay, so C, I'm actually going to move C over here. I think we might have enough room. So C, they say nitric acid, HNO3, and they give you a little hint. They said N is bonded to an OH group and 2 oxygen atoms. So we first have to draw the Lewis structure. So I'm going to say that nitrogen is going to be in the middle, surrounded by that OH group. So I will put the OH over here. And then it's bound to 2 oxygen atoms. So we have one like that, and we have one like that. So it kind of has the same structure as the nitrate ion. If you've noticed, this nitrogen has 2 single bonds and 1 double bond. The same thing with this nitrogen, a double bond and then 2 single bonds. The only difference is that this one has the H and this one has a -1 charge. So, and if that's the case, this will have the 2 electrons, this one will have the 3 electrons, 3 pairs of electrons, and this oxygen will have the 2 pairs of electrons if you've done the Lewis structure properly. So, here's my double bond. I have to play fair. Technically, I can have my double bond here with this oxygen, or I could have my double bond with this oxygen. Doesn't matter that it's bound to hydrogen, it still kind of has the same 3 atoms. So that's why you have to distribute this double bond to all of the same atoms. So this oxygen, this oxygen, this oxygen has to have their share of the double bond. And you gotta just keep in mind that the octet rule still applies. So if you still need to, what I'm going to do actually, if you still need A and B, pause the video right now because I'm going to just erase it because I just need a little bit more room here. So I will erase this all. Perfect. Let's just clean it up a little bit. And then I'm going to put this one up at the top and work my way. So there we go. We're going to draw resonance forms, so we need to bracket. So I'm going to just erase this. Bear with me, guys. Okay, thank you. All right, so bracket, arrow. And now I'm just going to redistribute this double bond to all the other bonds, right? So we have still nitrogen in the middle. Now this becomes a single bond. I'll throw the double bond here first on the right-hand side, and this still stays exactly the same. Now, if you've noticed, guys, resonance, you don't change any of the atom structure, right? If you've noticed, all of the, this one actually has only 2. If you've noticed, the structure, the backbone is still exactly the same, right? I'm not throwing like the hydrogen somewhere else or the oxygen somewhere else. You're just changing the bonds and the dots. You're just changing the electrons. So this would be one structure. And now you just have to make sure that this double bond gets over to here, right? So I'm going to draw my arrow. And nitrogen, will go back to the single bond. This will go to the single bond, and now I have the double bond here with its hydrogen. So if we're playing the octet rule, this needs the 3 valence electrons. Oop, and this needs the 3 valence electrons. Okay. This needs the 3 valence electrons. 3 pairs. Sorry about that. And this has just 1 pair now. So I'll put the 1 over here. And that's it. Box your answer off. And no charge, because HNO3 didn't have a charge, so that's it. And just notice that we didn't go into the hydrogen, because remember, hydrogen only likes to have 2 electrons when it's sharing. So you will never have double bonds with a hydrogen. So C is done. Now let's work on D, benzene, which is C6H6, and they give you this structure over here. So let me just recreate that. We have basically a hexagon of carbons. And we have hydrogens all around. Now, what's wrong with this picture that they drew you? Or that they provided, right? Well, none of the carbons have the octet rule. This carbon only has 2, 4, 6 electrons. This carbon has 2, 4, 6 electrons. So what did they give us, right? I think what they wanted you to figure out is draw the actual Lewis structure. For each of these carbons, there's still going to be 1 electron that needs to be paired. So when you do that, you will get double bonds. And you will actually have alternating double bonds. So double, single, double, single, double, single, and it keeps, like the cycle keeps going around and around and around. But now with benzene, let's see it. In my picture that I gave, I put the double bond on the left side for this, right? And then I have a single, and then I have a double, a single, a double, right? But could I have easily started my double bond on this side? Yeah, and that's where the resonance comes in. So I'm going to draw my line, and I'm going to bracket saying that there's resonance. And now the orientation of the atoms still remains the same. So they're all bound to the hydrogens. H. Sorry, I'm a little squished down here, but you guys get the point. And now instead, I'm going to have my double bond over here. Double. This will now be a single. Double, single, double. So do you see how it's basically like a mirror? But these are 2 resonance structures because the electrons are allocated differently. They're distributed differently. But the backbone still exactly remained the same. And for benzene, these are the only 2 structures for benzene because we just have this compound. There's no charges, so we don't have anything to do as far as making it more harder than what it is. Now for E. So what I'm going to do is I'm going to erase this. Let's see. Okay, I did a pretty good job. Just clean it up. Whoop. And now it looks like they did the same thing for E, which is the formate ion. So they gave you H, C, O, and O, but now you need to just fix it a little bit, right? There should be 1 more electron here because carbon has 4 valence electrons. So you just have to have the correct Lewis structure. So there would have been maybe 7 for that because we have the -1 charge. So if we've done this properly, I'm just going to erase this. We should have a single bond for an oxygen and a double bond for the other oxygen if we drew the Lewis structure properly. Now, can you guys see where the resonance is going to be? It's going to be between these 2 bonds because these oxygens are exactly the same. So, a bracket. And now, just like I put the double bond to this oxygen, I could have easily just put the double bond to this oxygen. So I will do that and just make sure that I have the octet rule. So here I have a carbon. The backbone stays exactly the same, right? The elements stay exactly the same. But now I'm going to make this one have the double bond and this one have the single bond. So with that being in mind, this now has the 3 lone pairs because it needs 3 lone pairs to get the octet, 2, 4, 6, 8. And this oxygen up top needs the 2 lone pairs because 2, 4, 6, 8. So that's good. The carbon still has the octet, 2, 4, 6, 8, so that's all good. And this one is done because I can't take that double bond into this bond because this is a hydrogen. Hydrogen never has double bonds. So that's the end. Bracket it off. They told me that it was a negative charge. It stands for a -1, so I have to keep that there. Let me just erase this just so that you guys don't get confused. But yeah, that's it. And that's the end for E. So this is how you draw resonance structures. You can only draw these if you're really, really, really proficient at your Lewis structures, because if you don't draw your first compound correctly, the resonance structures are not going to be drawn correctly. So it all stems from those Lewis structures, but you could always go back to number 40 through 45 of this chapter, and I will do them all with you guys, all right? So thanks for tuning in. Tell all your classmates about this channel. It will help everybody out. And I thank you for that. If you want, click the subscribe button to be in the know of when we drop our next set of questions. So that's pretty cool. Thank you for that as well. Have an awesome day. Happy studying. See you all in the next question. Bye-bye.